Okay, welcome back everyone to another installment on deep learning. This is going to be the last lecture that I give for a little while. I'm going to give another lecture in about a month on deep generative models, and that'll be in a little while. So last time we talked about kind of a general introduction to deep learning. We went through kind of the standard formulation of what is typically called a multi-layer perceptron. It's basically just a series of stacked one-layer linear classifiers. But today we're going to be talking about some extensions on top of that framework. So just to review, last time we said we would like to be able to learn nonlinear decision boundaries. So if we had some data like this, we saw that instead of actually trying to fit a curve to this data, we could actually cut it up with a series of lines and we'd still have a nonlinear decision boundary. So we saw that we could compose linear decision boundaries in order to get a nonlinear decision boundary. And the example we gave was this exclusive OR, the XOR gate last time, which we built using ands and ors. So the whole idea of neural networks, these artificial neural networks, is kind of a formalization for how to build these composed functions consisting of a bunch of linear decision boundaries. And we talked about how this is actually a universal function approximator. If you have enough units and enough depth that you can approximate any function. So that's a cool result, but it doesn't necessarily guarantee that we could find that function or that a neural network is our best bet for whatever data we're given. And we talked a little bit about this kind of geometric interpretation of what a neural network's actually doing. So if we interpret the dot product as the shortest distance between a point and a plane, then we saw that an artificial neuron is essentially calculating this distance. How far is this point away from my hyperplane? And that summation within this artificial neuron is that calculation of that distance, and that the nonlinearity was a way of transforming that distance into some other type of field. So if we're given this type of a distance, we can transform it and end up with a more expressive function, essentially. And we can compose layers of these operations and get out some general nonlinear function. So the general idea was just that we're going to cut up this space with hyperplanes, evaluate distances, and then we're going to transform these distances and then just repeat this process over and over again until we get to a space in which we can cut the data up with just a single hyperplane or a few hyperplanes and separate our data if we're doing classification. If we're doing regression, it's kind of a different story. So we're going to repeat this until the data has been linearized, essentially. And we talked a little bit about how neural networks, deep learning, has been such a hit lately because it's been able to tackle these really complicated domains like images, like speech, like sound and text, and also being able to handle both virtual and physical control tasks through reinforcement learning. And so in order to actually scale deep learning to these domains, you can't just take the naive approach of these standard neural networks typically. You have to actually incorporate additional inductive biases into these networks in order to actually get them to scale to very high-dimensional data on large data sets. So today we're going to take a quick detour and go very, very, very broad and discuss what are these inductive biases. It's kind of a buzzword. What does that actually mean? So inductive biases. So at its core, any intelligent system, anything that's trying to solve a task so these machine learning systems are trying to solve tasks at the end of the day. And in computer vision, that typically involves like object recognition, or perhaps object detection, or even object segmentation. And in the domains of text, sometimes we want to translate one language into another language, or we want to do some type of question answering scenario in which we're given a question, we want to come up with an answer given some database that we can query. And likewise, you can go into more control-related tasks where maybe you want to, the goal is to actually play Atari or the game of Go, or actually manipulate objects in the real world. And this idea of solving tasks actually is truly universal. It even applies to animals where the goal of an animal might be to survive and survive long enough to reproduce. And humans are kind of weird animals because we can actually come up with other tasks. Like right now I'm not really focusing on surviving, I'm focusing on teaching you guys. So there's a whole range of tasks that biological organisms can perform. So this idea of solving tasks actually gets kind of at the heart of machine learning. And the main idea you should take away, I think, from this entire course, especially this lecture, is this idea of the bias variance decomposition or bias variance trade-off. So any task, performing any task whatsoever, involves this bias variance trade-off. So let's unpack this a little bit. There are two components to solving any task. Two components that you can build into your system. One of them is some set of priors, which is also called bias. And another term is, or the other component is learning, which you can think of as the variance. So the bias is typically like how skewed is a model toward one solution, and the variance is how many different types of solutions can this model end up with given different draws of the data set. So what is a prior? So this is something that you've assumed beforehand. This is something that you've baked into your model. So this might be pre-training the weights on some other data set. So if you know that there's some other data set that has similar statistics, then maybe you can take some of those weights that you've trained on that other data set and actually just directly set them as the weights in your model. So you can just directly go in, set part of your model to be fixed as something else. You have a good prior on what those weights should be. If you want to maybe take a more relaxed kind of approach to it, you might set some general constraints on what those priors could be. So maybe I'm going to put an L2 regularization constraint on my weights. I know that I don't want my weights to be too big, so I'm going to try to constrain them because I have a general idea, a general assumption that these weights are going to be small for a good function. Very broadly, the entire architecture of the network is an assumption that you come into beforehand when you're trying to train a model. You come in and you say, okay, I think maybe this architecture would do well. That's some prior assumption that you're making on what type of function you think needs to be learned. And then there's also these ideas about, what kind of output I want the model to have, what kind of activations maybe should be in the model. If I'm incorporating dropout, then I'm incorporating some prior assumptions that, hey, maybe the features should be independent, more or less. They should be able to function without each other for the most part. So you see that actually the learning component of deep learning is only part of it. You have to come in and actually make some assumptions beforehand in order to train a model. So what is learning then? Well, that's something that you've extracted from data. From interacting with the data, you've extracted some information that helps you in solving your task. And we saw that this is generally in this paradigm of having some loss or some error, which gives you a gradient for your parameters, and then you can improve. So you do this kind of gradient descent optimization of your parameters, and then you're improving your function as you go along, hopefully improving on your task. And we drew this kind of a graph for how that might proceed. And as you're learning, you're shifting these hyperplanes in your neural network in order to section up the space of points more, in a way that's more conducive toward having the correct output. So we're shifting around these hyperplanes and cutting up the space in a better way. So that's essentially what learning is doing in these neural networks. And one thing that you should kind of take away is that it's really a balance. There's no right way to do things. So you could have a model with really strong priors where maybe you set almost all of the network weights to be fixed, and you only want to learn maybe a few additional weights. You only really care about some other additional weights. And the nice thing about this situation is, well, that's actually going to be really fast and easy to learn. And so you can deploy that model almost immediately. You just need a little bit of interaction with the data, and then you're set. But the problem is that if you make too strong of assumptions, or if your assumptions are invalid, well, then maybe your model is going to be too rigid, and it might be unadaptable to the data. So you might have like a suboptimal function for the task that you care about. On the other hand, well, what if we set really weak priors on the model? What if we said, okay, we're actually going to learn what kind of model architecture we want to have. We're going to learn some of these other parameters that we care about through repeatedly interacting with the data, coming back and forming better priors. Well, that's going to be incredibly slow and difficult to train. And so it's going to take a long time to deploy that model, and it might require a lot of parameters, and it's also going to, but on the bright side, this actually might be more flexible and adaptable. So if you don't know much about the data beforehand, you probably have to learn most of your function. You can't come in and just assume a bunch of things. So if you're approaching some new task, if you're given a data set and you say, hey, I want to perform this task given this data, well, then you have to ask yourself, what kind of performance do I want on this task? And then once you decide, okay, this is the kind of performance that I'm shooting for, then you can go and say, okay, this is the set of assumptions that I can make, and this is the amount of data that I'm going to need in order to learn the function on top of those assumptions. And you'd like to ideally find a set of assumptions, a set of priors, and a set of data that minimizes the time that it takes to actually deploy this model on solving this function. So it's this trade-off here with this scale between priors and learning. And one thing that I think gets kind of lost sometimes in machine learning is that a lot of machine learning is actually about the priors. The priors are actually more important than the learning usually. So you always have to make assumptions about the model. Almost always. You really cannot integrate over all possible models and essentially learn a model purely from data. This idea of like a data-driven approach is not entirely true. You always have to come up with some assumptions beforehand. And this even applies to biological organisms where when you're born you already have a very specific set of hardware that you come with, and your brain is not just a mush of neurons randomly connected. There's some very specific architectural constraints that your brain has. And so really you need to kind of be aware that a lot of intelligent organisms to begin with is priors. There's some organisms that are born, they already know how to walk, they can do essentially everything that an adult needs to know how to do. So we are all initialized from evolutionary priors, but the kind of cool thing about humans is that we seem to have a larger capacity for learning. So more of our lives is spent learning versus other animals. So potentially that leads to a more flexible, more adaptable organism, like we are. And just very, very broadly, if you think about kind of all of the systems that we as humans have built, every invention is essentially just priors. You have some prior on what a machine should do, like I want this piece of matter to produce light. Well, then you have to design it beforehand. You have to go in and actually design the light bulb or whatever it is you're working on. But the cool thing is that for the first time in history, we're actually creating machines that can learn from data. So if you have a really difficult task that you're trying to perform, like picking something up or recognizing an object, there's pretty much no way that a human can pre-specify how to solve that task. You can't hand design an algorithm to do some of these tasks. And so that's kind of the allure of machine learning, is that, okay, now if we have a good set of priors, we could learn from data on top of that. So just trying to put everything in context so you can kind of see that machine learning is just as much about having a good set of priors and a good set of assumptions for your model as it is about actually learning from the data. So today, we're going to try to incorporate some of these priors into neural networks. Specifically, we're going to discuss how to incorporate known structure about spatial and sequential data in order to impose priors, sometimes called inductive biases, on neural network models. So what does inductive actually mean here? Well, that just means inferring general laws from examples. So we're going to try to infer some general laws about spatial data, some general laws about sequential data, from looking at what properties do these data actually have. So we're going to be discussing, in the first part, spatial data, in which we're going to be talking about convolutional neural networks. And then the second part, we're going to be discussing recurrent neural networks, which are really good at handling sequential data. And this is going to allow us to learn models on really high-dimensional complex domains, and it's going to allow us to actually limit the number of parameters so that we can actually learn these functions. If we didn't make these assumptions, we actually wouldn't be able to learn these models in general. It would require too many parameters and too much data and too much time to actually train the darn thing. So without further ado, let's get into convolutional neural networks. So, say my task is object recognition, and I'll apologize to Yisong, but we're going to try to recognize Yisong.
Every year.
Yeah. And so what I'd like to be able to do is Yisong's my advisor. I'd like to be able to make a machine so that, if I see Yisong, I can recognize him and say, oh, okay, I need to, go talk to Yisong or whatever. And I'd like to be able to actually develop essentially discriminative mapping from some image that I have in order to an object identity, in this case, whether or not it's Yisong that's in the image. So if I'm given this image, all of the latent information about whether or not this is or is not Yisong is contained in the pixels in this image. All of that information is in this image currently, but it's not in a form that we can readily utilize to decide whether or not it's Yisong. So we need to extract this information and actually form a conditional probability, which is the probability of this being Yisong given this image. And this generally is referred to as inference. So if you hear about people talking about like neural network inference, in the typical deep learning sense, that just means forming this conditional probability of some latent quantity given some observed quantity. And you'll also notice that whether or not this is Yisong isn't the only information that is in this image. There's a lot of extra, what's called nuisance information, such as what clothes Yisong is wearing, what pose he's in, whether or not he's smiling, what the background is, all the lighting. Everything of this variety is also encoded in this image, and we actually want to be invariant to this nuisance image. So we don't want this kind of differences in pose, differences in lighting, clothes. We don't want these to affect whether or not we can say whether or not it's Yisong. So we'd like to be able to kind of be invariant to this information. And if I told you to just sit down and hand hard code a model in order to detect and classify Yisong, you couldn't do it. It's too difficult of a mapping. So we'll need to go and collect some data so we can follow Yisong's Instagram, we can follow his Facebook and collect a bunch of data. He posts quite a bit of it, so thankfully we can train a model. And then we can also collect a bunch of extra data that is not Yisong so that we can actually be able to distinguish between some other cases in which Yisong is not present. And so now that we've collected our data, then we can say, okay, what kind of model can we actually train? And so we need to figure out what kind of architecture we're going to use. So standard neural networks require a fixed input size, we talked about, so we'll have to figure out what kind of input size we can actually manage. So here's some general sizes that you might consider. The smallest image data sets are usually like 28 by 28 or 32 by 32. Some of the larger data sets can get up to images of like 1,000 by 1,000. So if you're given these sizes, you have to actually multiply out all the space dimensions, height and width by the number of channels. So here it's RGB. And so you're going to get a huge number of inputs. And so if you have larger images, well, you're going to have clearer patterns. It's easier to distinguish whether or not this is Yisong if you have a larger image. There's more detail there. But we're going to have more parameters. So this is going to give us serious problems if we try to make a model that's trained on very large images. It's going to require a lot of parameters. Oop. And if we conversely use very small images, well, we could get away with fewer parameters because we only have, in the smallest case, 675 inputs. It's not too many. But it's really unclear what these patterns are. So you really have to, I'm not sure that we'd really be able to distinguish whether or not it's Yisong if we were only using a 15 by 15 image. So we have to make some trade-off here, and we gotta think about this. One consideration I think is, well, actually the color channels don't really matter too much, so maybe we can make it grayscale. And then once we're given this, where we might decide, well, okay, 100 by 100 might be reasonable. You know, there's a lot of people out there. We got to be able to distinguish each song from other people. So what if we go with 100 by 100? So that's 10,000 input dimensions. So we talked last time about how neural networks require vectors. So we're going to have to reshape this vector into a 10,000 or 10,000 by 1 input vector that's going to go into our network. It's a lot of inputs. So if we think about this neural network architecture, we have 10,000 inputs. Then we have to decide, okay, how many units can we project that to? And eventually we're going to have to decide, okay, how many layers do you think we're going to need to actually go through this entire model? So how many units are we going to need in the first layer? If we think about, okay, the number of weights that we're going to have in that first layer is equal to the number of units that we have in that first layer times the 10,000 inputs. Remember, it's a matrix of weights that we're using here. So just a rough calculation, you can see that if we use many units per first layer, we're going to very quickly have an exploding number of parameters. And if we want to be able to detect, if you think about it, like just a few basic patterns at every single pixel location. So if we want to be able to kind of say, okay, there's an edge at this location, there's an edge at that location, things like that, that we might think, this is what the model probably is going to need to learn. Well, actually, the number of parameters is going to explode. And you see that it gets quickly above 100 million or more, and that's eventually you're not going to be able to actually train this thing because it's not going to fit in memory, and you would require too much data to actually train it. So, in order to actually reduce the amount of learning and the amount of parameters, the amount of data that we're going to need, we can introduce some inductive biases. And specifically, we're going to note some of the relationships that we see in spatial data. And so we're going to try to incorporate some of this spatial structure that we know about beforehand. So this is some assumptions, some priors that we're coming to the table with. We're going to try to incorporate that structure into the model. And hopefully that allows us to reduce the number of parameters and the amount of learning that we're going to need. So there's this idea of locality, which is that nearby areas tend to contain stronger patterns. Images are highly local, meaning that if I have a picture, the pixels tend to be similar, or if they're not similar, they tend to vary in very particular ways. So if there's an edge, that's a very sharp, discontinuous jump in the pixel intensity. If there's like a smooth gradient, well, actually it's going to be a very smooth progression of pixel intensity. But there's some very specific patterns, and those patterns are stronger if you look in a local region. Two pixels that are on opposite ends of the image are not going to be as correlated as two pixels that are right next to each other. That's just kind of a fact about spatial data. And you see this at multiple scales. So actually, if you look at larger scales, if you look at patches, you see that, again, you have some very specific characteristics that are shared, and when things do vary, they vary in very particular ways. So here I'm outlining the top of Esong's hairline, and you can see that this edge is changing in very specific ways. So you can actually note these patterns and how they're changing locally. And these patches do not have these characteristics if you look at patches far from each other. And then finally, if you look at regions, you can see that, okay, faces are actually made up of patches in very specific configurations. So you see that this actually, it operates over multiple scales, this idea of locality. So maybe we can build this idea into our network architecture and actually improve on the number of parameters that we actually need to learn. The other idea we're going to talk about is translation invariance. So this is the idea that it's really the relative positions of features that are important. The absolute position of a feature is not really important when it comes to spatial data. So if I take Esong's image and I move it around and translate it, then his object, or his identity actually remains constant. It's still a picture of Esong no matter where he appears in the image. So we can also take advantage of this property and hopefully build this into our network architecture. So let's translate these into our inductive biases. So this is kind of a case study of how one might go about doing this. In practice, it's really, really tough to actually note these structures and actually incorporate them into the networks. But let's build in locality and translation invariance. So this idea of locality. Again, nearby areas tend to show stronger patterns. So what we might think is that, what if we only looked at small patches? What if we, instead of taking every single input feature, we only restricted ourselves to a small window? This is where we expect most of the patterns to be, and we really don't need to worry about long-range interactions, at least not at a specific level in the network. So here we're talking about, okay, let's restrict the set of inputs, and you also see that by doing this, we need to actually maintain some sense of this spatial ordering. We're no longer going to reshape our vector, or reshape our image into a vector. We're going to maintain these spatial dimensions of height and width, and also of channels, and we're going to actually operate in more of the image space than some vector space, which is less meaningful when it comes to spatial data. The other idea that we talked about, remember, was translation invariance. So relative positions are important, not absolute positions. And so what we might think is that actually we could use the same set of filters throughout the image. So we don't have to learn a separate set of weights for each input. We can actually reuse the weights, because we know that an edge detector that applies to one part of the image is equally valid as an edge detector that's applied to another part of the image. So we know that we could share these weights and have actually a savings in the number of weights that we need. So here I'm showing that both of these orange patches, these lines coming out, those are supposed to be this exact same weights. Those are shared between these two units. So these are the inductive biases of what are known as convolutional neural networks. These have been around for a while, and the interesting thing is that they're actually a special case of standard fully connected networks. So let's see why that would be the case. So if you think about what we were doing before, we were reshaping our image out into a vector, and then we had every single input feature going into the next unit, or the unit in the next layer. So if we think about actually setting some of those weights to 0, well, then we could actually just get a convolutional filter. So you see that this convolutional filter here is actually just a subset of this fully connected kind of layout. And so by doing that, by actually saying, okay, I know that all these weights are probably going to be close to 0, or I'm just going to set them to 0, and I'm going to save on the number of weights. And now if we think about, okay, if we had multiple units in our fully connected layer that are both connected to all of the input features, well, if we think about, okay, what if we restricted the number of inputs to each of those units in the fully connected network, and then what if we made the weights be exactly the same? What if we set those weights to be exactly the same as each other? Well, then we would end up with this convolutional type of architecture. So you see again that the convolutional network is actually just a special case of the fully connected network where we've made some very specific assumptions about weight sharing and about locality. So we're getting massive weight savings here. So another interesting thing about this is that because we're sharing these small patches, these filters, we can actually have a network that's independent of the input size. That doesn't mean it's independent of the input features, but you see that because these set of filters are operating over the entire input, it actually doesn't matter what size input we're feeding in, because it's all shared. So that's kind of a difference that we get from fully connected layers, or fully connected networks, where we had to assume a very specific input size. So here's a cute little graphic. Place. Yeah. So this is showing you exactly what a convolution, a discrete convolution is operating in the image space. So here I have a set of filter weights denoted by this matrix right here. And that matrix is being dot producted with each input location. So taking the inner product with this filter at each location. And then you see that this output map here, in this kind of green color, is the result of that dot product. So I'm just multiplying and then summing. It's the exact same operation we're doing in fully connected networks. Here it's just you're taking a filter which has some spatial extent and also some number of channels. But we'll get into that in a bit. And what this is actually giving you is the degree of that filter at that input location. So it's how much does this filter agree or disagree with that particular location. Remember, it's this idea of calculating a distance to a hyperplane. And so we typically call the output of a convolution a feature map. So it's a map of where this feature occurs at the spatial locations. One thing that's commonly done in these networks is to use padding. So if you notice in the last slide, the output map is actually smaller than the input map. And that's because you can't actually perform a convolution if your filter is off of the input. So here we're showing, well, we could actually just put zeros around the perimeter of the input, and then that way our output is the same size as our input. So that way we're not actually decreasing the spatial resolution as we go. Now you have to kind of think about, from the network's perspective, you're essentially putting a black border around the image and telling it this is part of the image. So you might introduce some additional kind of weird things into the network, but this is something that people typically do in order to preserve the spatial extent of the image. Another thing that people sometimes do is what's called stride. So you don't apply the filter at every single spatial location. You might make some jumps. So here we're showing if you jump by 2 pixels as you're applying. So the typical case that we were showing was a stride of 1, but now we're showing we can actually move over by jumps of 2 if we wanted to, and compute only at some integer interval of pixels. And you didn't really see it from these last slides, but what we're doing is actually a convolution over multiple input channels. So this filter is not a matrix so much as it is a tensor. So this dark blue here is showing that actually this is a 3 by 3 by 3 filter. So you have 3 input dimensions here, or three input channels, and I'm applying a tensor here, which is just a multi-dimensional or a higher dimensional matrix on the input here. And then, so I'm taking this inner product of this tensor filter with the input channels, and then I'm still getting a single number out. And then each filter is going to give us a new output channel. So we'll discuss that in just a little bit. And then another very commonly seen operation is this idea of pooling, which means just locally aggregating values in each feature map. So if I give you this feature map and I apply pooling at each of these different quadrants here, and I say, take the maximum value that you find. Why would I do that? Well, maybe I want to do some amount of downsampling on the image, and I maybe want to build up some invariance. So maybe I don't care about the exact location of a feature, I just want to know, okay, is this feature here, yes or no? So give me the maximum value that you find. That's kind of an idea of, is it here? Is that feature there? And this can also be applied with padding and stride. And typically what you'll see is either max pooling or average pooling. So you're either taking the maximum value or you're taking the average value. Last week there was a question about, isn't this kind of a non-differentiable operation, taking the maximum of something? Well, actually, we're not learning how to do this pooling. This pooling is totally predefined, so we can actually just take, what was the maximum value that we got, and then we just backprop into that maximum value unit. So let's do a quick little pop quiz. So if we had a 5 by 5 input feature map with 16 channels, and we convolved it with a set of filters, each of which are 3 by 3, and we got out a something by 36 channels output feature map. Then if we used unit stride and no padding, then let's take a second to think about this. How many filters are there? How many filters did we apply to this input feature map in order to get an output feature map hint with 36 output channels? 36. We had 36 filters, each of which gives us an output feature map. So the number of filters in a convolution is the same as the number of output feature maps that you're going to have. And what is the size of each filter? So we already know it's a 3 by 3. What is the other dimension of these filters? 16. Yes. So each of these filters has to operate, at least in the standard convolutional setup, on all of the input features. So that means that each filter is going to be a 3 by 3 height and width spatial extent that is operating over all 16 input features. So each filter is a 3 by 3 by 16 tensor. And then finally, what is the output filter map size? 3. Yeah, so if we only applied the convolutional filters at these valid locations, so if we only applied, so if you see where the cursor is, at this location, that location, this location, then you see that there's actually this 3 by 3 grid here in the center where we can actually apply the convolutional filters. If we were to try to apply it at the edge, well, actually the filter would not fit because it would bleed off into the edge, and we said here we're not adding any padding. So you see again that if you apply convolutions without any padding, you're going to actually decrease the spatial extent. So we went from a 5 by 5 down to a 3 by 3. So that's kind of a general introduction to convolution, and we've seen that this is going to help us actually reduce the number of parameters in our networks and actually allow us to learn models on very high-dimensional, complex data sets. So just kind of a brief history lesson was that some of the earlier natural image data sets actually came out of Caltech. This was about 15 years ago, quite a while ago actually. So some of the first natural image data sets were things like Caltech 101 and Caltech 256. So here you have 101 object classes that were just pulled off of images from Google search. Same with Caltech 256, but now it's more object classes. And then later on, you got into these data sets called CFAR, which just stands for Canadian Institute for Advanced Research. And you get into these CFAR data sets, which are many more images. So now we have 60,000 images with 10 classes. So this is kind of analogous to MNIST, but now we're looking at natural images. So you have things like truck, and you have things like horse, classes like that. And then there was also the CFAR 100 data set, which is now 100 object classes, but still the same number of images. And then you get into these very, very large image data sets like ImageNet, which have millions of images and thousands of classes. And so it was really a lot of advancements in, now people are posting all of their images to the internet. And you have things like Amazon Mechanical Turk, where you can actually pay people to label images for you online. And you can build up these very massive image data sets, which has really been one of the driving factors in promoting a lot of the recent research in deep learning. And it's only grown since then. There's massive data sets now where you just scrape essentially all of YouTube and try to learn models based on that. And so let's talk about some of the models that have actually come out of this. So one of the early models was this thing called LeNet. It was developed by Jan LeCun, and he clearly named it after himself. But he trained this model on MNIST and digit recognition. And this was a pretty big deal back in the late 80s and 90s. And people were thinking, wow, these convolutional neural networks are amazing. They're actually able to do some of this image classification on larger data sets than people had worked with before. But it really wasn't actually until quite recently that people were able to actually train some of these larger models on natural images, because in order to train a large convolutional network, you actually kind of need, on natural images, you need a lot of images, and you also need a lot of compute. So it wasn't really until people started putting these models on GPUs that we saw things like AlexNet in 2012, which was kind of a breakthrough architecture that performed much, much better than previous techniques on that ImageNet data set that I talked about. And from then on, it just kind of snowballed, and people were coming out with bigger and badder architectures every year. So you had VGG, and this thing called GoogleNet, ResNet, Inception v4, ResNext, and DenseNet. So I won't go into the details of all of these networks, but just broadly, the networks have gotten deeper in general, and you see like here we have these residual connections that we talked about last time. There's been a push toward actually breaking out each individual layer into multiple sets of convolutions, so you're operating not just on a 3x3, but you're also using a 5x5 and a 7x7, for instance. And then we had these concatenated or dense connections that we talked about last time, where now every layer is looking at every layer before it. And so these have all had some small improvement in image classification, and have kind of pushed the field forward. And then likewise, there's also been a number of models that have been developed for things like object detection and segmentation and key point estimation. So the kind of earliest model that used deep learning to actually do object detection, where we're trying to figure out, okay, where in the image is an object, was this thing called RCNN, which just means regions with convolutional neural networks. And the basic idea is just extract a bunch of regions from the image, pass them through a deep network, classify them, and whichever ones are really highly classified, then just return those. And then there was this thing called fast RCNN, which says, actually what I'm going to do is just feed in the entire image, extract some patches, and just classify those. So it's now much, much faster. You don't have to feed in a bunch of different patches. Faster RCNN, the main idea was just, I'm going to learn a network that figures out where I should probably look for some of these patches of where objects might be. And mask RCNN, which just adds segmentation to the loop. This thing called YOLO, which stands for you only look once, so as opposed to some of these earlier detectors where you're actually feeding in a bunch of different patches, classifying all the patches, this YOLO model is just what's called a single shot detector, where it actually only feeds in the image once and then just outputs directly a set of boxes of where it thinks objects might be. So this is much, much faster than these other two-stage detectors, but it doesn't perform quite as well. And then for segmentation, there's things like fully convolutional networks, where now you're actually taking something like one of these deep models trained on classification, and then putting some extra deconvolution layers to upsample the image to some type of segmentation mask, where you want to segment out each object. Something like the hourglass network, where you're actually downsampling the image, then upsampling, then downsampling and upsampling, and trying to actually get out some idea of where key points might be on like a human pose. And then things like this UNet, where you actually have multiple layers of, or multiple resolutions that are all combining to give you some output segmentation. So what you want to do for segmentation is actually have some idea about high-level concepts about like, okay, this is where this object is, but you also need to still capture the low-level details of, okay, this is where that line is that I need to segment. So this has had some pretty dramatic results, and you can see that we're now to the point where we can train models to pretty clearly segment out things like cars, pedestrians, you can see potted plants, and this has actually been like kind of huge, because really before deep learning this would not have been possible. So this is a clear new task that we can perform. It's also had effects like being able to segment out or actually localize human key points. So here you have some people walking around and dancing. And again, this is only applied on each individual frame, but you can see that it actually performs quite well in being able to figure out what is the pose of this person. So it has to detect, is there a person here? And then it has to say, okay, here's where all the body parts are, and here's how they line up. So it's actually quite impressive that it can handle such large crowds of people like doing these outrageous movements. Okay. And then we haven't really talked about it yet, and I'll talk about this more when I give the next lecture on generative models in about a month. But convolutions can be also applied to image generation. So instead of taking an image and trying to extract information, you're taking some representation and trying to generate the image pixels. So one popular model is this DC GAN, which we'll talk about GANs, but it's essentially just trying to take one part of the model here and take some noise vector and transform that into an image, and then the other part of the model here takes that image and tries to classify, is this or is this not a real image? So the way you train this is you feed in sometimes real images, sometimes these fake generated images, and then by backpropping all the way through this network, you can actually learn what makes a good looking generated image. Likewise, there's convolutional varieties of variational autoencoders, which is another very popular form of generative model. And then you have things like autoregressive models like this thing called pixel CNN. And we'll get into the details of all these in that lecture. But I just wanted to show you, there's a really, really cool video showing what these models are capable of doing. So these are all generated images from noise, and it's just trying to mimic the distribution of celebrities' faces. So this is the cool part here. So they take walks in this latent space. So they shift around the latent vector, and you can see that the face is also changing. So you can make these walks in this latent space. It's pretty cool to visualize. I hope I haven't given anyone nightmares. So we'll go quickly through this, but the convolutional layers, it might be natural to wonder, okay, what features are they actually picking up? Are they doing something sensible? And you can directly visualize the first layer of features because these are actually operating in the image space. So if you visualize, okay, what is the first set of features doing? That's really pulling out different kinds of color combinations and edges. So, okay, that's reasonable. I won't get into the details of how you visualize some of the higher features, but there's one technique called deconvolution. So here we're showing the images that are maximally being activated by some particular set of features. So this is the second layer of a popular network out there. And then if you use a deconvolutional neural network, you can actually go back and look at what parts of the image were actually maximally activating that feature. So here's what the deconvolution looks like for the second layer. Here's the third layer patches. And you can see that as opposed to this earlier set of filters where now we're picking out, maybe we have like an edge here, an edge there, some set of like colors, like, maybe some reds and reds up here, greens here. Here we're getting into, a little bit more complicated shapes. We're actually pulling out, some curves, and we're pulling out maybe some black object here in this corner, some blue sky with a skyline. And you can see that that's roughly what's being picked out by these filters. As you go deeper into the network, you start to see things like, Okay, we're pulling out circles or like bigger curves on speedometers and clocks. We're pulling out dogs' faces and more dogs' faces and things of that variety. So it's getting more and more complicated features as we're going through. And then you eventually get to the point where you can pick out really specific patterns like keyboards and lemons and more flowers and dogs' faces and things like that. And then there's another technique actually where instead of visualizing the top image, what you might do is actually just optimize, say, if I wanted to maximally activate this particular feature in the network, how would how would that image look? So you're going to do optimization of the image space. We talked a little bit about this with adversarial examples, but here we're just trying to optimize one of the internal features. And you see that if you optimize one of the earlier layers, you can get images with a lot of these kind of like lines. And you get more and more complicated patterns as you go through. So there's a lot of different techniques for doing this. I'd really recommend looking at this blog post here by Chris Ola. He's phenomenal at explaining how do you actually visualize some of these features. And another idea we didn't really talk about is that you could just as equally apply convolutions to sequence data. So we're going to talk a little bit more about sequence data in just a bit, but if you've heard of WaveNet, it's the generative model that is running on your phone if you have Google, like an Android, that's generating the speech. So this is a generative model of speech that uses convolutions over previous inputs to generate the next output. And then there's some interesting extensions of this work where you can actually apply convolutions in non-Euclidean spaces. So up to this point, we've been talking about maybe you have some height axis and you have some width axis, but what if you had like a mesh object and you wanted to apply convolutions over that? Well, there's extensions where you can do that, and generally if you have any type of graph data, then you can also apply convolutions to that graph as well. So there's some cool things you can do beyond images. You don't have to just work with images. So just to recap, we talked about exploiting spatial structure in order to impose inductive biases. We talked about how we can incorporate this idea of locality and translation invariance into the network. We're going to cut down on the number of parameters. And so what we're essentially doing is reducing the flexibility of the network in reasonable ways. So we're kind of handicapping the network in ways that we know it'll still probably work well. And that allows us to actually learn these features, as opposed to if we were using a standard neural network, it probably wouldn't be the case that we could do that. So we can actually scale these networks up and perform these tasks, given some data set. Admittedly, the data set still has to be large to learn a complicated set of features. So now let's talk about recurrent neural networks. So the task that we care about now is for instance, something like speech recognition. So if I have some input waveform that comes in, and I want to say, this is the characters that are being spoken right now, then how would I go about doing it? I want to map the input waveform to some sequence of characters and recognize the speech. Again, this input waveform contains all of that latent information about what is being spoken. And again, we want to form this discriminative mapping about, what is the probability of some text sequence, some sequence of characters, given this waveform that I have. And again, we see that there's some nuisance information that we want to be invariant to. We don't want to care about things like, the characteristics of the speaker's voice or the volume or some additional background noise. We'd like to be able to be invariant to those features and only select out the latent quantity of what character is being spoken or what text. And again, it's way too difficult to actually define this by hand, so we're going to have to go collect some data. So you might collect, people saying typical things like, "Okay, Google," or "Hey, Siri," or I'm not sure what they say to Alexa, but I yell Alexa maybe. And again, we have to think about, okay, what network architecture are we going to use for this? Now, sequential data has this added complexity, which is that there's really variable size. Depending on how long of a sequence you spoke, you could have a variable length output and a variable length input. And so how are we going to decide how many input features we're going to need if we had a standard neural network? And it would be really tough to actually do this. So you might be sitting there thinking, well, okay, we just talked about how convolutional neural networks, they actually can operate on any input size, so why don't we just use them? And as we saw, yes, you actually could use convolutional neural networks here, but you have a fixed input window size here. So you're actually only able to look over a certain set of features. And so that might be a limitation if we wanted to pick out maybe patterns that are across many, many steps in the sequence. So we may be able to actually exploit additional structure in the sequential data in order to impose these better inductive bias, in order to restrict our model in maybe a smarter way. So let's discuss what is the structure of sequence data. Again, you also have this idea of locality. So patterns tend to be formed, in local regions. So if I say one word, there's a certain probability distribution of the next word that's going to come after that. And then there's also this idea of translation invariance, where it doesn't actually matter where it was spoken in the sequence in order to recognize it. There's the relative patterns are what really matters again. But unlike the spatial data, you only have this single axis along which these extended patterns occur. So you might have patterns within a single time step here, but most of the patterns that we're really going to care about have a natural ordering to them, which we might be able to actually use if we want to build better models. So in order to actually process this data, we may want to actually mirror this structure. So we can process the data sequentially. And this is the general form of how you might go about doing it. So you have some time direction here, and you have some set of inputs, which is again a sequence. And you might map that each input to a hidden value, and then those hidden values are connected across time steps. So here we don't have to worry about having some convolutional window. You could potentially connect any input node to any later node. So we could have an effective input size of potentially infinite, and we also, again, fix the number of parameters because the purple set of parameters are all shared, the green set of parameters are all shared, and the pink set of parameters are all shared here. So we've restricted the number of parameters to a fixed size, even though we could have a potentially infinite length model. So we can express this mathematically, having some hidden state, which we call h. So the hidden state at time t is just some nonlinear function of this linear decision boundary applied to both the previous hidden state, so that's what this green arrow is denoting, we're applying this across time, and the input x at that time. So I'm just here with these brackets concatenating the previous hidden state and the input state, and that's going to give us our new hidden state. And then the output is, again, the typical, linear mapping with a nonlinearity applied. And that's applied on the hidden state. So again, these are a special case, actually, of standard neural networks, where we've imposed some very specific skip connections and some very specific sharing of weights. So if we have this recurrent network, we could actually unstring this and kind of stretch it out, and if I show it in this way, you can see that actually this is a fully connected network. But here I've just unrolled it in a very specific way. So let's look at what's happening here. So I have the first time step that gets fed in to this node here. Instead of feeding all the inputs into that first node, I'm only feeding in the first time step. Now I take the second time step and I feed it into the second node, and I feed the first node into that node. So you can see that I've built up this actually feed-forward network, but it has this nice recurrent property because I've put very specific conditions on where things are connected and which weights are shared. And you see that actually depth here corresponds to the number of steps. So we could have a potentially infinite depth function if we wanted to. We could unroll this infinitely. So because this is actually a standard case of feed-forward networks, we could use standard backpropagation to actually train it, which in practice is what people typically do. And so you have gradients that are passing through from, if you're calculating a loss at each of these output nodes, you have gradients that are flowing back through the network So you have gradients coming from potentially each output, and then gradients are being applied through time steps. So this is called backpropagation through time. And the primary difficulty that you encounter with recurrent networks is that it's incredibly difficult to propagate information over very long time horizons. It's incredibly difficult to find these very extended temporal patterns. So if I had some input node here that was really, really highly predictive of some output node at a much, much later time step. For instance, if I'm writing an email to somebody and say, hi, my name is Joe, and then I yada, 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 have a very lengthy email, and then at the end I sign off, you know, sincerely, comma, and then what should be the next set of characters? Well, in order to actually predict that, I would need to look at the very, very beginning of the email. So I have these very, very long, extended temporal patterns that I would like to be able to pick out, but it might be difficult to propagate that information all the way through the model. So one reason for this is because you have these, remember we talked about vanishing gradients, you can equally have exploding gradients if your derivative of your nonlinearity is greater than 1. If you're multiplying a bunch of terms over a very, very lengthy sequence of time, you could eventually have a gradient that explodes. And then there's also a huge memory and computational footprint to actually training these models. So one naive attempt that we might say is, well, actually, what if we just connected everything internally? Then information is just guaranteed to propagate. And you know, we're just going to skip connections all over the place. It's going to work. But actually, that increases the amount of computation because now your input vector, or your hidden vector, is going to have to operate over a huge number of inputs from previous time steps. And you're going to have to set some limit on the window size. So what people have typically done in order to solve this problem is actually add a trainable memory module to the network. And you can think of reading and writing from this module, which we're going to call for right now a cell state. So don't be scared, but this is an LSTM. This is a long short-term memory module. And it follows these set of equations. There's different variants of an LSTM, but we're going to just discuss this kind of basic implementation. And we're going to walk through all of this. But off the bat, you can see, again, okay, you have an input fed in at each time. You have these states coming from the previous time steps, this H here and this C here, which are being propagated across time in this orangish kind of hidden cell, or hidden unit. And then you have this output here again, which just goes to your output Y. So what is going on in this mess of arrows and circles and all that stuff? So off the bat, we should just say, okay, we have a new hidden state, which is called a cell state. So this is our memory that we're going to read and write from. And you see that this is propagated just through time across horizontally here. And likewise, we also have a hidden state just as before, which is also propagated across time. So ht minus 1 eventually becomes ht. So the first thing we have is this forget gate. So this forget gate is saying, okay, this is the things that I want to kind of cancel out from the previous cell state. And so you're taking in your input, xt here, and you're taking your previous hidden state, ht minus 1, passing it through this forget gate, which is just a nonlinearity again, applied to your linear decision boundary. This nonlinearity is typically the logistic sigmoid in order to have a 0, 1 kind of being able to say, I want to keep this entirely or I want to remove this entirely. And then after or in addition to this forget gate, you also have an input gate. So this input gate is also taking in the previous hidden state and also taking in the current input. So you have these two gates here. And if you remember, we talked about kind of these highway networks and residual networks. It's a similar kind of idea where we're using some gating here to selectively allow information through the network. So again, we have this input gate takes in these parameters and again, usually mapped through a logistic sigmoid from 0 to 1. Now the cell state takes in some new information here that's coming through this hyperbolic tangent applied to the previous hidden state and input. it says, okay, I want to keep some of that new information, so I'm going to element-wise multiply that with my input gate features, and then I'm going to element-wise multiply the previous cell state with the forget gate. So I'm going to keep some of this old information with my forget gate, and I'm going to incorporate some new information with my input gate. I have these two gates that are controlling this information. And in addition, we also have this output gate. And this output gate is going to help us in figuring out the new hidden state, the H subscript T. So this output gate is just another gate, just like our input and forget gates. It's another gate with a linear decision boundary and a nonlinearity applied. And what we're going to do is actually element-wise multiply that with a nonlinearity applied to the cell state. So we're just going to say, okay, we're going to keep some of the cell state, or modulate the cell state in some way, and that's going to be our new hidden state. And just as we had before, we're going to pass that hidden state into our output. So you see that at a very coarse level, it's very much the same as our previous formulation of recurrent networks, but now we have an additional cell state from which we're reading and writing information to. So now if we actually wanted to, we could train this network to learn how to keep information. We're not going to be overwriting information at every single time step, potentially. We could say, hey, I want to keep this in memory. This is a name, for instance. I'm going to need to hold on to this name. If it's the beginning of the email, hold on to that name. I'm going to need it at the end of the name when I sign off. So in practice, these networks are incredibly complicated. I will admit it's kind of ridiculous that these things actually work in practice, but they work incredibly well. Any neural network that's used in industry, any recurrent network, is typically an LSTM or a variant of it. This idea of having a memory module from which you can read and write is hugely important. So there's been some follow-up work in this area of memory. Although I would say it's an extremely underexplored area. If you want to get into it, it's very ripe. We talked a little bit last time about hot field networks. So this is this idea of being able to actually encode in the set of weights the ability to address memories through content. So it's this idea of auto-associative memory. If I give you part of the input pattern, you can complete it. So this is actually a dynamical system, as are all recurrent networks, and you can do this auto-associative memory where I say, Mary had a little blank, and then you would be able to propagate this network and eventually spit out land. And then a kind of a simplification of the LSTM is this gated recurrent unit, which also typically works quite well in practice. People started using what are called neural Turing machines, which have a more explicit separation of recurrent network from memory. So you have here these read heads and write heads, which are writing from a bank of memories. And I won't get into the details, but there's a lot of really cool new areas that are being explored right now in memory. One such area is memory networks, where you take each input, encode it into a memory bank that you maintain, and then for instance, I can give you a query like, where is John right now? If I've given you a paragraph that says, John went to the park and met up with Mary, and then Mary left and John went to the roller skating rink or something, then you can figure out, okay, this is actually where John is by looking into your memory bank. And then more recently, there's been this idea of a differentiable neural computer, which is actually just a fancier version of the neural Turing machine. But now there's this improved ability to not overwrite other memories. So you have actually separate, independent memory locations, and then you also have this idea of being able to have pointers within your memory in order to say this memory, corresponds then to this other memory. So it's these temporal pointers. And we've really only discussed some very basic kind of ideas for recurrent networks, but once you get into this idea of recurrence, you really have limitless opportunities. You can have, the standard feed-forward network is a type of, you could think of that as the simplest recurrent network, but you could have maybe one input that gets fed over multiple time steps to many outputs. For instance, I give you an image and you want to generate a caption for it. This is what people will do. Or maybe I give you an entire sequence and you want to classify one thing, like was this a positive review for the movie, or was this a negative review for the movie? I want you to give you the sequence and then you tell me the answer at the end. Or maybe I have a sequence of English text and I want to translate it into French text. I might do this kind of machine translation setup where I feed in an entire sequence, I get to the end, and then I say, okay, spit out the French equivalent of it. Or maybe I have this final kind of scenario where now I'm saying I want to classify part of speech, for instance, at each word in a sequence of text, and so I want to spit out like a noun, verb, things like that. Good. Another cool dimension you can explore with recurrent networks is adding additional depth. So you can actually have stacked recurrent units that feed into each other. And in practice, these are what people typically use in more real-world applications because these have a better ability to form more abstract representations. There's also this ability to do this autoregressive generation, where now the output gets fed back into the network as an input. So recurrent networks are not necessarily autoregressive, but that is a very popular choice of how to operate them. And you can, for instance, take in a sequence of text and generate, okay, what is the next word that's going to be spoken? And so you can form these language models where you're actually forming a generative model of language, of text. And you can train this. This is an example taken from Andrei Karpathy's blog post on this. It's actually not very hard to train these character level RNNs in practice. And so you can take in, like, here you took in Shakespeare and generated, here's a new set of Shakespeare dialogue and narration. So it doesn't always make a lot of sense. It's kind of a cool thing to do, though. People have explored this for music generation and a bunch of other areas involving sequences. And even though we talked mostly about sequence data for RNNs, you could equally apply this autoregressive generation idea to images. Images don't have necessarily a natural ordering, but you could impose one if you wanted to. And for instance, you could take in all of the previous pixels that were generated and then just generate the next pixel. And you could condition this generation on those previous pixels. And in practice, you can generate some pretty good-looking images. And these models are actually highly competitive for generative modeling these autoregressive models. And we're going to talk about this more in the next lecture that I give. So, just to recap, what have we done today? We've used additional priors. We've made some assumptions about the structure of data to impose additional priors on the model. And these are sometimes called inductive biases. And I would stress that these inductive biases are essential to actually getting these models to scale to real-world data. Standard neural networks often just don't cut it for high-dimensional data. And it's really this balance you have to think about of how much data am I going to need versus how many priors can I impose on the network. This idea of pre-trained weights, for instance, is one way of imposing additional priors and really reducing the amount of data you need. And why is any of this important? Well, we live in a spatial temporal world. These data modalities are hugely important for our world, because that's the kind of inputs that we operate on. We have streams of spatial sensory inputs, whether it's touch or vision or sight or sound, and you're constantly receiving these types of spatial temporal data. And so it's hugely important for getting real-world embodied intelligent machines out there, is being able to process this type of data. So these CNNs and RNNs are the building blocks of building more intelligent agents And one example, for instance, is this recent work where they combined a CNN that's taking in visual input from an agent exploring a maze, and it's trying to optimize some reward that it's getting, but it's also predicting what reward it's going to get, what the value function will be, and trying to also control the pixels that it's seeing. And so if you look at what the agent's doing, it's pretty incredible, and it's all facilitated by recurrent neural networks and convolutional neural networks. You wouldn't be able to process this with a standard feed-forward network. Yeah, for whatever reason, whenever I see these agents exploring these mazes, I'm just amazed.
Do the signs on the wall mean anything?
So I think they're very specific to allow for like better features, but I don't think they have any significance necessarily. So here you're actually fighting some enemies, which is kind of cool. And here, so just to wrap up, this is a visualization of what the agent is actually kind of performing as it's going through. It's trying to predict a bunch of its inputs, and also it has this replay buffer on which it's replaying previous episodes that it's seen in order to not forget what it previously saw. So if you want to build up any more complicated system, you really have to use these low-level building blocks of convolutional networks and recurrent networks. Okay. And that's all I have.